All right, so today we'll be talking about our last classification model, support vector machines. And then at the end of it, we will talk a little bit about pipelines. So a lot of this material is actually adapted from that textbook that I keep talking about. So again, very good textbook if you want to take a deep dive into any of these algorithms that we talked about so far. We're going to talk about SVM. There are several different layers to SVM models. So first we'll be talking about the maximal margin classifier, which is sort of the base SVM, I guess, followed by soft margins, which we'll see takes misclassified things into account. Then we'll talk about the kernel trick, and then we'll walk through an example. All right, so support vector classifier. The whole intuition behind the support vector classifier is with your data in space, what you're trying to do is you're trying to find a plane that separates the classes in feature space. So literally, if you have like a 2D feature space, you're just looking for the best line to divide your data. Kind of similar as decision trees where you're trying to find best splits, but instead of splitting per dimension, we're trying to find a plane. So imagine in 3D space, you sort of have like a big flat sheet of paper that's dividing your data, and that's what we're trying to find, the best dividing plane. So if you can't successfully separate your classes in your feature space, you can do one of two things, and both these things we'll talk about how they're applied in SVMs. First, you're going to soften what we mean by separating. So again, you maybe allow for some to be misclassified, or we're going to enlarge the feature space so separation is possible. So this later we'll talk about it very, very briefly because mathematically it's quite complicated, but talk about conceptually what that is. Enlarging the feature space, and that's what's known as the kernel trick, which I have here as one of the bullet points. So we'll talk about that in a bit as well.
So Ish, so we're dividing it with a plane.
Mm-hmm.
I don't understand how we're in 3D space though if we have a bunch of
so
our own dimensions.
Yeah, so imagine we have 3D space, and let's say, actually let's use this. I know this is a 2D version, but imagine you have a 3D space with 3 features, x1, 2, 3, and then the colors will denote what class they are in. Mm-hmm. So quite similar to this, and in this case we found a perfect split where this line perfectly splits your data.
Okay. If
this is expanded in 3D, instead of a line that separates your data, you would have to have like a 2D object separating your 3D plane, if that makes sense. Imagine if you have like a box and you want to cut your box in half. That would be the plane that separates your data.
Right.
Does that help? Yeah. But yeah, the thing is, what determines that plane? It will take every feature into account because the formula for the plane is very, very similar to, it actually looks very similar to your linear regression formula, where it's actually a linear combination of all of your features that determines where the plane is. Okay. I don't know if that's getting too mathy, but yes. Awesome. So, all right, let me zoom back in. So support vector machines are sometimes used as a general method that incorporates the maximal margin classifier and support vector classifiers. So these things are actually slightly different, and I'll talk about them in a little bit. By definition, a support vector machine is a support vector classifier utilized with a nonlinear kernel. So this is where we get a little bit more nitpicky with the terminology. We do typically just say support vector machines as like the model, but more specifically, support vector machines are only used, support vector machines correctly as a term are used for when you have a support vector classifier with a nonlinear kernel. And we'll talk about nonlinear kernels later as well. So there, when the support vector classifier, SVC, is combined with the nonlinear kernel, and we'll talk about those later, the resulting classifier is a support vector machine. So in scikit-learn, and I don't think I have it hyperlinked here, but let me just pull it up. In scikit-learn, when you're using support vector machine, it's actually called an SVC, and you'll see here you can define the kernel. And the kernel, if it's nonlinear, it actually turns your SVC into a support vector machine. If you're using just a linear kernel, it's still a support vector classifier. So that's just like a really nitpicky terminology thing. If you call it an SVM, even though it's using a linear kernel, people probably won't, I don't know, hate you for it. I don't know. So yeah, so the idea of this is you're trying to find a hyperplane that divides your data. Something that I personally just thought about, I don't know if any one of you are thinking this, what if you have more like multi-class problem? I honestly have not looked into how the calculation of SVMs work with multi-class data. So I'm actually going to do a little bit of reading on that and like let you all know. But we're going to just deal with, we're going to just talk about binary classification problems. You can put in multi-class data into this model and it'll still do the classification for you, but I'm just personally not too sure how the math works. Like instead of a plane, do you have like 2 planes? I don't know. So that I will get back to you on that. So in a p-dimensional space, how do you define the hyperplane? The hyperplane is defined as this. So you can see here, I don't know, let me zoom in a little bit more. You can see here, you have all your x's, and then you have your betas. So again, like I said, very, very similar to your linear regression formula, but it's not exactly the same. It does have what looks like an intercept. But if you were to plot this out, because it is equal to 0 here, you actually get a plane in your n dimension space. So just so you know, what you're trying to actually find are these coefficients. You're actually very similar to linear regression and logistic regression. You're trying to find the best coefficients that best divides your data. So that's what we're trying to optimize for, these best coefficients. So there we have it. The vector of all the betas is a normal vector to the hyperplane. And then all the points on one side is greater than 0 and on the other side is less than 0. A couple of very mathy terms. I will say that if you don't understand what this is now, it's fine. It gets into a little bit of linear algebra. But what this is saying, that this vector is a normal vector to the hyperplane. If you have your vector of your coefficients, what it means to be normal to the hyperplane is if you have your dividing hyperplane, let's say my hand is the hyperplane, anything normal to the hyperplane is any vector that sticks out 90 degrees from the hyperplane. And that'll actually come back into play later when we look at the cost function. But yes, any questions so far?
Excuse me? I kind of get used to see our target variable in y-axis, but in this case, we have different features, right?
Yes, absolutely. Yeah, you're
and,
right.
Why we are separating them? Because we already have them separated in our data frame, right?
Yeah, so in our data frame, usually our data is not this clean. Let me see if there's another, I wonder if there's another example down here. Yeah, for example, our data will probably look more like this rather than easily divisible. So the idea is to just find the best line that divides this data into 2 classes. Yeah, and again, yes, you're right. These are 2 different features and the Y is denoted by the color of the points here.
Okay, got it, thanks.
You're welcome. Anything else? Okay, so a couple things we're going to be talking about. How do we fit this hyperplane and the different levels in which the SVC turns to an SVM. So in this data that looks very nicely separable, this would be the best hyperplane, right? Because you have all the pink class on one side and the blue class on the other side. But typically that's not what our data looks like. So as a first step, we'll talk about the maximal margin classifier. And the maximal margin classifier tackles the problem of classification directly in a sense that it doesn't compute a probabilistic model. Instead, it constructs a hyperplane to directly separate the classes. So just like I was mentioning before, you're trying to find the best hyperplane here. So with this, and with this specific data set, you can see all the blue points are here and all the pink points are here. This looks pretty separable. Problem being that you can actually fit multiple hyperplanes, right? With a bunch of like different angles of tilting and a bunch of different like shifting of these 3 lines that we have here, we can have a lot of different hyperplanes here. But how do we choose the best one? So let me zoom back into the text. The problem is that we can come up with an infinite number of such hyperplanes as we can tilt the line back and forth and it would still serve the same purpose of classifying your data, right? So therefore, how we choose the best hyperplane is we choose a hyperplane such that it would be the farthest from the training observations on either side. So what you do is with each hyperplane, and let's go with this middle one first, and let me get my annotator. What you do is you measure the 90-degree distance from each point to the line. So for example, with all of these red points, and let's first look at this plane first. The distance would be computed by taking all of these distances. And usually it's like a mean squared error, a root mean squared error kind of distance. And then of course, these have to be 90 degrees because if you're familiar with, I guess, geometry, the shortest distance between a point and the line will be the 90-degree distance. So that's the distance that's computed. Basically, you want to find the line that results in the furthest distance from all the observations on either side. So that means you're going to add up those distances. You're also going to add up all of these distances. And then I guess between all of the planes that are possible in dividing this data, you would just find the one with the maximum distance. And again, it is also done by gradient descent. You are adjusting the line or the plane by changing the coefficients beta that we had in our hyperplane formula before. So it's a process of gradient descent, just like that. Questions so far? All right, so the distance between the training observations and the hyperplane is called the margin. So the margin here, usually the margin is referred to as the shortest distance that you have on either side. So for example, with that middle line, and let me just redraw that one more time. With this middle line, the margin would probably be this wide, because I guess these look like the closest points. Your margin would probably be somewhere around here. So another way of saying this is we are looking for the maximum margin possible. That's just another way of looking at the best hyperplane. Questions about this part? All right. So here you can see, oh, literally the same drawing. Let me zoom out a little bit. Same drawing we had. These are the points that are the closest. And so this would be the width of our margin. And the margin is something that we can also keep track of. And again, the wider your margin is, the more separable your data becomes, or the more separable your data is. All right, so again, these are just the math formulas that define the maximum margin classifier. You have this sum of your betas being equal to 1. That's just a constraint that allows your plane to act like a plane. And then you have this just being maximized. And the M is the margin that you're trying to maximize here. Not super important right now to go through this math, but if you're interested, there is a building SVM from scratch lab that honestly myself took a few hours to go through it. But if you're really interested in how the SVM works and the calculation of it, it's actually a pretty fun like math exercise. But again, if you feel like you're falling behind currently, don't recommend doing that right now. All right, so these examples with the maximal margin classifier, these are all for data sets that have a separable plane, they are separable in such that you can construct a plane that perfectly separates your data. In a lot of cases, we don't. So therefore, we introduce the soft margin classifier. So even though maximal margin classifier sounds like an intuitive idea and isn't too difficult to optimize for, might not be desirable under these two circumstances. First, it'll be pretty sensitive to individual training observations. You can sort of imagine that if you have a different train set, your margin is going to shift. And also the algorithm just won't converge if your training observations are not linearly separable. So for example, over here, what happens if we can't come up with a hyperplane that perfectly separates the training observations like these ones above? So first, our solution would be the soft margin classifier, where you loosen up your definition of a margin. So in this example, where would you even put the line, right? You can sort of see maybe it's around like here. but we don't know. So rather than seeking the largest possible margin such that every observation is not only on the correct side of the hyperplane, but also on the correct side of the margin, meaning that you have every point on the correct side, we're gonna instead allow some observations to be on the incorrect side of the margin or even on the incorrect side of the hyperplane, which makes sense, right? We allow for some points to just be on the other side. One prevents overfitting as well. Yeah. So this just changed your constraint slightly. Again, this is what changes. Instead of m, you have m1 minus eta, and eta is just like a very small number. Again, wouldn't worry too much about this for now. So in this case, and let's see, the hyperparameter eta is known as the slack variables that dictate how many observations we allow to violate the rule of margins or the hyperplane. So basically, how many points are allowed to violate the classification line. EI tell us where the ith training observation is located. So if I is equal to 0, it's on the correct side of the margin. If I is greater than 0, it violates the margin. And if I is greater than 1, it's on the wrong side of the hyperplane. So then the value C is the sum of all of these E's across all the observations. And C will pretty much control the bias variance trade-off of this statistical technique. So you imagine if you are constraining all of your errors to be smaller, you will allow for less misclassification. And if your C is greater, you allow for more slack in your classification, which is exactly what this is saying. So how do you determine the ideal C value? You can see here, again, you have many different possible combinations of like separation planes with different margins that you can potentially use to split the data up. Yeah, any questions so far?
So quick question. So like high value of C means you're allowing for a lot of violation, which means that you're not going to have like a perfect split, so, right?
Yes.
So in these graphs, the highest value of C would be something like
perhaps this one. Wait, no, this is on the right side. I'm going to look for points that are on the wrong side of the margin. So here you can see that there are 2 points here in the blue zone. Here you can see that, yeah, this one's only 1 point. This has 1 point. Yeah, so probably this one, which has, yeah, this one will probably have a higher value of C.
Okay.
Yeah, but it will also be the individual E values are also computed by like the distance away from the plane.
Okay, that makes sense.
Yeah. All right, so what they'll do is they will just fit this plane and the margins based on these constraints here, which is very similar to what we were doing the maximal margin classifier, just that you get to control how much slack you have. Let's see, question, is there any way to tell it a preference of which class to be on the wrong side? Ooh, that I'm not too sure. I imagine, I don't think so, at least not with the basic SVMs or SVCs. I'm not too sure. Let's actually take a look at this. Maybe there's something with the, oh, here, class weight. I imagine with the class weights, you might be able to rebalance the class to maybe look at one more. So here it looks like, all right, if you have a class imbalance in your data, doing this class weight will rebalance your data. But it also takes a dictionary. So you might be able to give it a dictionary to re-weight one class more than the other if you want it to be more sensitive to a specific one. Yeah, that's probably the one you would use to control for that. All right. Okay, so we've talked about the maximal margin classifier that works great for perfectly separable data. We've introduced the soft margin to allow for some slack, but something else that that is actually what makes SVMs really, really powerful, is something known as the kernel trick. And so here you can see, oh, yeah.
Before we go on, I wanted to ask about the graphs.
Oh, yeah.
In the first graph, it looks like it has the largest margin, and you're saying the second graph has the largest C. So I was just wondering how directly related the two were.
Yeah, that's a good question, because typically if you're in the margin, overall your your E values are smaller, and then because you have, oh, you're right. I guess I saw these. I read these wrong. Yeah. So this, for some reason, I don't know what I was looking at, but yeah, this would definitely have a higher C value. You're right, or a higher C value. Just because you have all of these blue points in the pink area. I was somehow thinking that like these, if you had like points that were on the wrong side of the hyperplane and also outside the margins, those would have much higher values of C, even though you have fewer points, because it is also weighted by the distance. But yeah,
So
thanks for clarifying that.
The C and the margin are directly related. A larger one will do a larger the other?
Because, you know, with these values of like it being between 0 and 1, so the distance is computed with relation to the margin. So your error is rescaled to be between 0 and then 1, if that makes sense. So the scale of your distances are controlled by your margin here. I don't know if that makes sense. So if something is on this margin line, it would have a error value of 1. And if something was on here, it'd be 0, and it's scaled accordingly. So therefore here would be, even though these margins are different, between this region, it would be 0 and 1. And so therefore having these dots on the outside will be a greater value contributing to C, if that makes sense.
Okay, thank you. You have my permission to continue.
You're welcome. You're welcome. All right. So yes, now to get to the kernel trick. Sometimes we have data that just can't be separated even with the softer margin. So this is just an example of one. If you have like either class, you have one class on either side of the other class, you can't come up with something linear to separate them. And so the idea of what we're doing here is, again, this is just to show that it doesn't make sense to construct a line between this data. What we do here is we enlarge the feature space through the use of a kernel and then fit the SVC in the enlarged space. And so imagine what we can do here is we can take this data and just create new dimensions. And hopefully in these new dimensions, you can then separate the pink from the blue. And then you can probably imagine when we recompress the data, we'll end up with a nonlinear boundary. So this is just a hypothetical example. Let's say we can take these blobs, and in creating a new dimension, we're able to say that, all right, in 3D, and let me attempt to draw this out. So in 3D, oops, I thought those were going to be straight lines. But let's say this is the new dimension, and this is x1 and x2. Let's just say we have, and let me get these drawn. So let's just say we can get our red or pink points here, or purple, I'm not too sure what that color is. And then we happen to have, oops, oh, the X's are always red. All right, hold on. And then instead we have our blue points like here and here. So just imagine we created this new dimension that happens to separate our data that way. Once we have that, we can fit our SVC to this data, and then we'll probably get a plane that looks something like this, that cuts it halfway like that. And then when we recompress it, our decision boundary is going to look something probably like this. Or it perhaps could even look like a circle like that. So it really depends on how this new dimension is constructed and compressed. I won't talk about the specific math of expanding dimensions, because I personally am not very familiar with that either. But you can trust that there are a couple built-in kernel features that will test the expansion of dimensions in different ways. And usually that is a hyperparameter that you can tune as well. I mean, that is a hyperparameter that you can tune as well. Questions about this part? It's a little bit abstract, thinking of like expanding dimensions, but the idea is you expand the dimensions such that your data can be separated. And then when you recompress your dimensions, you'll get a non-linear looking decision boundary.
In
Questions about
any
this?
visualization libraries, can show us a contour line between more than two-dimensional ways?
Oh, good question. Like if I had like a 3-dimensional feature space and I wanted to see the decision boundary there.
Yeah.
I'm not too sure about 3D, honestly, because I know that scikit-learn does have the decision boundary visualizations. I'm not sure if they work in 3D, to be honest. Usually what people do is if you have, for example, if you have 10 dimensions and you want to show your decision boundaries, you would actually use a dimension reductionality technique. So for example, and I'm going to talk about this sometime next week really briefly. For example, you could use something like PCA. And what PCA does is it takes your 10 dimensions and lowers it down to 2. And each of your 2 new variables will be a linear combination of every other feature, each of your 10 features that you had previously. And then you sort of have like a compressed version that you can 2D map out. So I imagine if you had like high dimensional spaces, that's something you can do to visualize your decision boundary. But in terms of 3D, I'm not, off the top of my head, I don't know of one, but not sure if you can actually take their 2D example and expand it.
Okay, thank you.
You're welcome. Anything else?
So what exactly is like a kernel?
Yeah, so the kernel is the formula that allows your dimensionality to be increased. So right here, I'm just gonna very briefly talk about a couple. So, oh wait, before I get into that, this is an example of a non-separable data set. If you have something like this, how am I gonna fit a plane through my data? And this is like a very, very common visualization. Could have pretty much showed this instead of trying to draw what I was trying to draw earlier, but what you can see here is they're just creating a new dimension to separate this data by. And so once you separated that, you can imagine that the decision boundary for this would probably be a circle in between these 2 circles here. So back to Teju's question of what is a kernel. These are all different kernels. Oh wait, these are all different kernels where you're actually making use of the inner product. I'm not going to go through this because it goes through a lot of like math theory, but this is here. This is also copied from the textbook that I recommended. So feel free to look at that. I would say that in interviews when asked about SVMs, if you're able to talk about how it's trying to fit a plane to divide your data, as well as perhaps something about increasing dimensionality and then dividing it, that turns out to be sufficient. So yeah, typically people don't ask about the math behind kernels unless you are, I guess, a machine learning engineer that designs kernels. But yeah, the kernels are literally the mathematical functions that help to expand your data space. So different types of kernels. And again, like even to me, some of this looks like just letters. There's a radial kernel. The radial and the polynomial kernel are the ones that are built into SVM. And literally what you do here is you would plug in your data and this function will transform your data into one with more dimensions. And as you can see here, the main kernels that you have here are linear, which is the SVC kernel, polynomial kernel, RBS stands for radial, sigmoid kernels, and pre-computed kernels. So if it's pre-computed, I believe pre-computed, you get to give it a kernel, I think. But yeah, this honestly, at this stage of like where you're on your data science journeys, this just happens to be something that you tune. And typically, one of these kernels will perform a lot better than the others. Question about this? Yeah, kernel is literally the mathematical function that will expand your data into more dimensions. All right, any questions about SVMs before we move on to implementation? All right, in implementation, I'll also show you all later a way to time how long your model takes to train. So here we're importing our usual libraries, and just so that we know later, I'm importing time from time because I'm going to use a timer object in a little bit. So this is a CSV that we have that is on banknote authentication. I'm going to add these headers. And again, I did get a question about this at some point. I forget who it was, but these are just these are the features used to predict on whether a banknote has been authenticated or not, or is authentic or not authentic. Yeah. So this is not the variance of the data set. So not too important what the context of our data is in this case, but we're going to do our chain test split. And what we're doing here is we're going to use SVC for now with a radial kernel. So what I'm doing here and what I wanted to point out, and probably will be useful for you in your projects, especially if you want to also take into account how long a model takes to run. This is something that's pretty useful. So this time object, what it does is if I call time, it will literally give you the exact time in like, I think, milliseconds. So if I just call this right now, this is the time in like milliseconds of like currently. So you can imagine once I rerun this, this number is going to increase. You see it ends at 7423, now 7433. It's been about 10 seconds. So this is in seconds. So with this, you can see here that I'm starting a time with tick. I'm going to fit and run my model and make predictions. And I just want a time to see how long that process took. I'm just going to have another variable that's, again, the time when that executes, so I can find out what the runtime is. So in terms of the classifier, same syntax as all the other scikit-learn ones. You have your instantiation step, your fit, and your predict. And this took 0.006 seconds to run. I will say this is also a very small data set comparably, so SVMs usually take much longer. Then just really quickly take a look at our scores. You can see that with even with our test data, perfect predictions, which is awesome. Questions about implementation or this time thing that I just talked about? All right, so overall, SVM is very effective. However, it's not very interpretable. It's a little bit harder to find out what the most important features are. Although I believe you might be able to pull out something there. Here. There is an article that talks about important features in SVCs, and I will send that out to you. I forget right now which one it is. But yeah, optimization is a little hard to understand, especially when you have kernel. And it performs really well on high dimensional data sets with smaller number of observations. And so the intuition behind that is you can imagine if you have a lot of dimensions and fewer observations, it is easier to find plane that will divide your data better, just by the nature of having more dimensions to look through or more ways to tilt your plane. So yeah. Any closing questions on SVMs before we move on to pipelines?
This is kind of a general one beyond it, but I know you can extract the probabilities. And is that just like the overall probabilities between the train and test set?
I am not too sure off the top of my head. It could be, I think it could be like probability of it being one class or another. Or it could be I can't think of, yeah, it probably is that, but I'll look into it later as well. SVM
Right.
is not something that I've used too much. So I'm not too sure of what all the attributes are.
And you can't change the threshold for something like this. It's pretty much just in logistic regression, correct? Because everything else is just kind of like averaged out, and that's what the decision is.
Yeah, that's right. Because with logistic regression, you're fitting your curve, but you get to adjust your decision boundary. Something like SVM, what you are fitting is the boundary. You are fitting the decision boundary. So that is not something that you can adjust. That is already optimized with your data, with your kernel.
Cool. Thank you.
Yeah, I'll look into those attributes a little more. SVM is probably the one that I have used the least, just because it takes, I would say it's one of the longer training time algorithms, but definitely one that's very interesting to look at. All right, so really quickly with the last 20 minutes, I want to talk about pipelines, and pipelines are something that are used to speed up, or I guess make more efficient your machine learning process. So as you can see here, all I'm doing that is new here is I am importing pipeline from scikit-learn.pipeline. So what a pipeline is used for is if you have multiple steps in your data, like from getting to your raw data to making your predictions, if you have multiple steps, especially if there are steps that require scikit-learn libraries, you can turn it all into, you can put them all into a single pipeline. So most common example, you probably want to scale your data if you're testing models like KNN or logistic regression. So if I want to scale my data, what you can do is create a pipeline like this. So a pipeline, which is this pipeline object here, also needs to be instantiated, and you instantiate a pipeline with the steps that you want it to go, that you want your data to go through. So as an example, I'm going to use the standard scaler followed by the support vector classifier. And how it takes in the data is it takes in a list of tuples. So first, you can see in this first tuple, I have SS, which stands for standard scalar, followed by the actual standard scalar object. This name here can be whatever you want, and we'll see later how this comes into play. You can actually extract the standard scalar object by using this key. And I'll show an example of that in a little bit. And then here I have my, my classifier. So again, it is a list of tuples that go into your pipeline when you instantiate it. So once I have this instantiated, I can straight away fit my trained data, and then I can test my test data. So because we know that the SVC has a perfect prediction from earlier, let's just try a different one. So with this one, we're going to use a random forest classifier, and I'm going to also show you how you can incorporate it with grid search. But before that, we have our scaled pipeline 1. And the way that we can actually pull out specific things, so maybe you want to see what some of the probabilities were. So if I do this, scale pipeline 1, and I pull out my SVC, so it kind of works like a dictionary where I call the key and I get return the value. If I do this, I actually get my SVC object. I actually have this classifier. So any of these attributes, so maybe I want to take a look and see what the coefficients are. I can literally do this, scale pipeline 1, look for the exact classifier object, and then pull out my coefficients. Oops, is it coefficients? Oh, only with linear kernel, right? So let's, as just an example, let's use support for now, just to show that we can pull out information. There we go. So we have our support here. This just to show, I don't know, I forget what support is exactly, but just to show how you can extract the information from specific parts of your pipeline. Questions so far?
So you could make a pipeline for basically all these different classifiers and then just like go through running those. And then if you need to tune like hyperparameters, would you make a new pipeline that had different hyperparameters?
So the next example I'm going to show is doing a pipeline with grid search as well. So I'll walk through that right after this. But yes, I think a pipeline would be most useful if you have, usually if you just have a scalar and your classifier, you can, I feel like doing a pipeline doesn't exactly like, it doesn't reduce the number of lines of code that you have. But if you're doing a scalar and then you have a smote step, perhaps you have also like an imputation of like your null value step. And then your classifier, you would have 4 things that you can have in your pipeline. There is no limit to how many things you can have. So you could have all those steps in one single pipeline. So if you have like scalar followed by smote, and then your classifier, that will also work. And you will set it up in exactly the same way in the order that you want it to be done as well.
So is this kind of like defining a function that would do all these things?
Kind of, yeah. Yeah, because you can see here with this pipeline, you're doing the fit on your train set, you can technically also, I'm not sure if you can transform, I forget. But yeah, you can do the transformation. Let me just do a quick double check. I believe you can also transform, there we go. You can fit transform your data as well. And I guess you can't get the transformation, but if you were to predict on your test set, all you have to do is call .predict. And the reason why I don't have to do a transform is because in this step where I'm doing the, not score, but let's do .predict. What did I do here? There we go. If I did predict, I don't have to worry about oh, there we go. There. The reason why I don't have to transform my test data first is because I'm having it go through the pipeline and it automatically knows to transform my test data with the standard scalar parameters of my train data. So it saves you a couple steps like that. So with grid search, what you can actually do is you can put your pipeline into grid search. So you don't put your grid search, you don't grid search on your pipeline, you put your pipeline into grid search. I don't know that, I think I said it incorrectly. But what it is that you can first set up your pipeline. And let's say I want to do my random forest classifier. I can, in the same way with normal grid search, set up my grid. And this syntax is just to keep track of which model's grid I'm using. So I can set this up this way. And then with this grid search, you can see here that I'm giving it the grid and the estimator is my entire pipeline as well. So you would put the pipeline into grid search for a single model to find the best parameters. So just to do it really quick, I'm going to reduce the number so that it's not going to take super long to run. But yeah, so this will get you your best parameters for that model. So yes, you can use it with grid search. Questions about this so far? Cool. There are many different ways you can make use of pipelines and grid search. It's really up to you to figure out what works best with your project. I will say I personally didn't use my pipeline in the training step because I didn't use that many. I actually didn't use a scaler for my project when I was doing this. However, I did create a pipeline for the final product just so that if I had any like unseen data that I wanted to import from elsewhere, I can feed it through the same pipeline so it does all the data cleaning steps that I needed to do. So usually what I do is after I figure out what the best parameters are, I just create a new pipeline that is just the best parameters and I can use that. You can see here I have all those steps. I can have my train confusion matrix, my test confusion matrix. You can see it's actually doing pretty well. And then I get, for example, future importances. So cool. Pipelines are not a necessity in this project, but would be cool if you tried it out. It's not something that you need to have, but definitely might work to your advantage. Cool. Any questions about this? All right, if there are no questions about this, I wanted to show you all like just an example of how I functionalize my code for the project. Don't copy my code because if you do, I will know. But this is just a quick example. So just for a little bit of context, this is a natural language processing project, but I use all of the same models. You can see here in this notebook, I have like KNN, I have all my tree models, I have my boosting models, so on and so forth. So doing exactly the same models as you are doing, just on a different data set. But what I did here was I created this function that would just do everything at once for me. So what I did here was have it taken the model and the name just so I can keep track of all the results. And what I did was I saved all of the metrics for my training set and my testing set. So you can see here, I'm also making use of the time object to find out what the training time is and what the testing time was. So basically for any model, I will save all of this information. It's up to you. You don't have to write a function that does everything in one step. For some people, it might work better to have many smaller functions. but this is just an example I wanted to show you. And why this was great was because for each of my models, I could just do this and I get all my results. And at the very end, I could put them all together and I have a pretty neat table that I can just like at one look, I guess not at one look, but I have all the results in one place. So I don't have to keep scrolling up and down and comparing my models. So this is just one way you could functionalize your code. And you can sort of see here as a preview, boosting models take a long time because as we learned yesterday, they are running model after model. And yeah, again, bag trees because you're fitting a bunch of trees at the same time. Again, boosting models take longer. Naive Bayes, because it's simply probabilistic, they run pretty fast.
So I'm kind of
yeah.
confused as to like what the difference between making that function would be and then creating a pipeline.
Yeah. So a pipeline, you're still going to have to do like, oh, actually, let me go back here. With your pipeline, you still got to do your pipeline.fit to score your pipeline. It's still another set of steps. So technically what I could do also is I could instantiate this pipeline and use it with my function.
Okay.
Yeah, but the main thing is the thing that a lot of people repeat, a lot of the code that a lot of people repeat with this project are the metrics. And with your metrics, I would prefer not to see just like the same like print accuracy score, print F1 score, rather write a function that does that.
And you can't include the metrics in the pipeline. That doesn't make any sense.
Yeah, exactly. In the pipeline just gives your data a place to go, but it doesn't score on its own. So you can see here even, yeah, the score would be a separate step.
So you're just going to prepare it and then put whatever classifier you want on it, but you can't like add to the pipeline to like fit it and then predict and then print out your metrics. You can't do that.
Exactly. Yeah, exactly. I mean, you can in separate steps, but yeah, because you run into the same issue if you're just going to be doing that code over and over again.
Okay.
Yeah, basically, whenever you find yourself copy and pasting your code a lot, you can probably write a function.
Got it.
Yeah.
So that function that you wrote is actually, it's running the model too, because it's counting the time of how long the model runs. I functionalized like all my metrics, but it doesn't actually run the model. So how did you put that in there?
Yeah, so this one, because I had it in my no, not this one. XGBoost, I had to write a separate one because the data didn't work. And I don't know if any of you have run into XGBoost issues. I did link that article yesterday. But yes, most people, I think, and it's definitely fine if you just have it like having it save all your scores. But yeah, what I had here was I literally have it taken a model object. So you can see here, I instantiate this KNN model, and then it takes in that entire model object. And then what it does is it takes in model here, and then it just does the model.fit. So whatever the input model is, it can fit my X train and Y train. Yeah, I will say because there are some models that take your data in differently. I did not account for this in my project because NLP is a little bit less, it was a little less relevant, but things like logistic regression and KNN, you might want to scale. Other ones you don't have to, so you might want to have different functions to account for that. But yeah, for me, this was the easiest way that I saw it. Also, just to take note, I did this like about a year ago. I did not do this while I was doing my project as a student, so definitely took some time putting this together. But yeah, this is basically how I did it. I just had it taken the instantiated model variable for it to run the model within the function.
You could then do that with like a pipeline though, right? Like you could run the pipeline through your model if you wanted to.
Yeah, that's right. You can also have it, yeah, you could pretty much like, if you wanted to, you can have it taken a model and have the model create the pipeline maybe in here and then have it taken a model. That's also possible. And then like just put in the model at the correct part of the pipeline. Yeah, that also would work. But up to you all to explore. Yeah, in this project, I didn't even use a pipeline for this one. But yeah, just wanted to share like an example of how you can functionalize some of your code. I would like to see everyone at least try to write a couple functions. You don't have to do anything. You don't have to do things to this level, but yes. Cool. Any other questions? Ooh, I forgot to mention, I got a question about when to smote your data. So as you all have seen with that mini project data set that I gave you all, it has some class imbalances, but it's not a super serious class imbalance. I believe it's like around like a 70-30 or maybe 80-20 split. I would say a good time to smote is if you see your model predicting the majority class. Like for example, if you have a confusion matrix that returns you like all zeros in the right column for predicted one, if you see that occurring, it's a very, very sure sign of maybe smoting your data to rebalance your classes. Or if you just see your model not predicting too much on the right column, and usually one is the minority column. So if you see patterns like that, that's usually a sign to smote. If your model is still performing fine on your heavily imbalanced data, it could be just that, you know, your data is more separable. For a lot of the models, it works that way. If your data points in space are just further apart, the two classes, you might not have to smote, but those are just some things to look out for if you're deciding whether you want to smote or not. Or maybe just try it out to see if it does improve your model or not. Cool. One more thing to remind you all, do let me know what data set you want to do for this project. And again, do look at the project prompt. Tomorrow, I'll be formally going through all the things to look out for this next project. I also have like a guidelines document like I did last time. This document is actually going to be shared across the two cohorts, so there will just be an abundance of questions and notes that I'll be taking across all the office hours that I think will be helpful. And yeah, I'll be putting out the poll in the class channel. Do look through the data sets and pick one of them, or if you want to do one of your own, just let me know. Any final questions to close out? Cool. Well, I wish everyone a happy Wednesday. Any questions that you come up with from now till, I guess, the next study group, just let me know. All right. With that, wish you all a good rest of your day and hopefully get some good work done. Bye, everybody.
Bye.